Welcome to our first lecture in mechanics of materials. So the basic assumption behind the mechanics of material is that we assume, and actually not assumption, that's the reality, that many or majority of material, they act like a spring. When you apply force to them, they become elongated. When you release it, it goes back to its own position. And the reason for that is because of the crystal structure. So if you look into a structure of a material, they are all those bonds together, so they are united. When you apply force, they like to stick together. When you release the force, it comes back to its original shape. Now, in a tensile stress machine, we apply force in the two sides of a specimen, and then what we observe this graph. So the graph that I'm showing you right now is for mild steel, or something which is not very brittle, which is not plastic. Remember, all the plastic, they could have different curve. Now, for what you could see a region from when you apply the force, and then again down here on the y-axis, I have the force that I apply. On the x-axis, I have the elongation. So the phenomena we see if you increase the force, it becomes elongated, but the relationship is linear, and that's what we call it elastic region. Before you reach to a yield point, again, this area that we call it linear region, and then we reach to the yield after that. So again, in majority of our design, we don't want to get into the sigma yield. And by the way, when we apply the force, because we just want to make it generic again, and I apply the force depending on, is this thick like this pen, or is thick as much as my arm, right? Could be any types of thickness in between. So that's why, in order to create a unified types of unit, we use something called stress. So instead of using force, I divide the force by the cross-sectional area. I call that stress, or sigma. So that's sigma. And then in the other side, I divide the delta L by L, and I call that epsilon. Now, on the linear relationship, again, as I say, sigma is the stress, and then epsilon is the strain. And the slope of this line, if this is sigma, this is epsilon, we know the slope of this line is E. So the slope of this line is E, meaning that E is modulus of elasticity. So basically, what I could say, again, in a spring, we can say F is equal to K delta X. Coming back from physics, if you apply the force to spring, if I have a spring like this, and I apply a force to it, I know this will be elongated for a distance like delta X. The K is the spring constant, or the stiffness of the spring. Now we can have the same equation for materials. So we call it sigma is equal to E epsilon. E stands for toughness, stiffness. We call it modulus of elasticity. It is a factor of how elastic a material is. If you have a very high E, meaning that whatever you apply the force, it just becomes elongated for little, right? And then in the other side, I have a material that it could elongate it a lot more, which is like milder types of material, but it go back to its own position. Now, what I do, I'm going to use this equation, which is the Hooke's law. In the Hooke's law, we can say instead of sigma, I'm going to use F over A. Instead of epsilon, I'm going to use delta over L. Again, I use the delta with this shape like this. If I cross multiply the equation, I'm going to get sigma is equal to FL over AE. So A delta is elongation, how much it become elongated, or displacement, whatever you want to call it. F is the force, L is the initial length of the specimen, A is the cross-sectional area, and E is modulus of elasticity. Now, we could have different cases. We could have tension, and we could have compression. In the compression, obviously, the delta would be coming, my bad, this is supposed to be delta, not epsilon. So there you go. Delta is equal to FL over LE. It could be in compression. Again, in compression, delta is negative, and then could be on the tension. So let's look at this example. In this example, I have a wire with the metal wire diameter is 2.5 and 2 meter long. So by just looking at this, I do understand that they give me the diameter, because if I look into a wire, I can see two characteristics to it. It has the length equal to 2 meter, and the diameter is 2.5 millimeter, and this is the diameter. If I apply the force along this, the force of this is along, and then this has been stretched for 0.3. So I'm assuming I'm applying the force in this direction, and then I have the delta for a stretch as 0.3 millimeter. So by looking into this, they give me the diameter, they give me L, the force is 12 Newton, and the delta is 0.3 times 10 to the power of minus 3 meter. Remember, that was millimeter, we converted to meter. So question asks me the stress on the wire, which is sigma, and also a strain in the wire. Easy calculation, you can put the force over area. Again, how can I calculate the area? I have the diameter, and I know area is equal to pi r square, or I can say pi d to the power of 4 divided by d to the power of 2 divided by 4. Again, there is a divided by 4 here, which is missing. Hopefully I consider that in my calculation. Then you can calculate the area. As for, again, once you found the area, you already have the force, which is 12. You divide it by the area. This will give you your answer. In the other hand, for calculation, for calculation of the epsilon, which is the strain, we use the delta over L. Delta is 0.3 divided by 2, and then that will be the amount of strain that we have. Again, strain looks like a percentage. It doesn't have a unit, but the unit for sigma, because you put Newton on the top and then you put meter at the bottom, the unit for this will be Newton meter. Sorry, this is supposed to be positive 6, not negative 6. Now 10 to the power of 6 is mega, and then Newton over meter is Pascal. That's the unit for Pascal. So that's why we use 2.35 megapascal for it, for the unit. The other example I have is a steel specimen has a cross-sectional area of 100 meters square. This time they give me the area. I don't need to go through the calculation to find the area. It's already given to me. And then the length of the gauge is 50 millimeter. The gradient of elastic section is 410 times, again, they give me the force with respect to the length of it. Determine the modulus of elasticity. So basically, what they say, the gradient of elastic sections, which is Newton over meter. So this is actually some sort of Newton per millimeter. We call it F over delta. So meaning that for every delta, how much force you have. We've got it elasticity gradients, or how much it become elongated for that delta. So F over delta is this much. The area is given to us. Then we can move on from there. The length is given too. So we can say, again, what the question asks us, determine the modulus of elasticity. So I have a bunch of stuff I need to cook. So as you can see, I can say delta is equal to this. Again, I can get into a place from the equation sigma is equal to E epsilon. So I work with this equation. Instead of sigma, I put F over A. Instead of epsilon, I put delta over L. You just kind of cross multiply them. You get to this relationship. E is equal to F over delta times L over A. Then F over delta is given to me. I'm going to put it here, which was like 410. But the unit was Newton per millimeter. I converted that to meter, Newton per meter. So I multiply that by 1,000 to get rid of that. Again, this is a dimensional analysis, right? You have 1,000 millimeter up there, 1 meter down here. Then out of again, you have 1,000 here, 1 millimeter down here. That's how much we got for F over delta. And then I have L over A. L is given to me. A is given to me. I'm going to put them there. and then finish my calculation, I'm going to get 2.05 10 to the power of 11. Usually we report E in the units of gigapascal. Again, as I discussed before, units for again pascal or gigapascal or whatever unit we want to use. For pressure, we have two sorts of units. So the SI unit for pressure, stress is actually types of pressure, right? The same as pressure because it's force over area. If you are in the SI system, we use Newton over meter, we call it Pascal, right? If you are in the English system or Imperial or American engineer system, we use pound per, this is a Newton per meter square because it's pressure, right? It's force over area. So pound over inch square. And we call this PSI, meaning that pound per square inch. So the unit for this, if you go to a kilo, we use kilo PSI, or we call it KSI. For this one, usually the Pascal is a very small amount, assuming that you put 1 Newton over 1 meter square, which is not much. The pressure that we like right now, the air pressure that we live on, is 100,000 Pascal. So that's why it will go to a unit like megapascal or gigapascal for E. And in this case, I have gigapascal. Okay, let's do a static problem. And then in this case, I have a lamp which attached to 2 wires. And what the question give me? The question give me that I have the length of each of these wires. That's given to me. So actually, let's read what the question asked me. The diameter of AB and BC is given to me. The question asked me to determine the average normal stress. So just do a little bit of thinking. Normal stress is force over area. You gave me the diameter. From diameter, I can find the area. But how can I find the force? That's where we go back in static. We have a 2D equilibrium problem. I have the weight of lamp. I'm going to draw the free body at point B. And that's going to be here. At the point B, I have one force that's going down. That's the weight, 80 times 9.81. Another reminder that because the force is, the mass is in kilogram, you have to convert it to Newton. I multiply by 9.81. And I have 2 forces for each of those cables, FAB and FBC. The angle for one of them is 60 degrees. The other one, they give me with the ratio of 3, 4, and 5 in this little triangle. Then I can actually break them down to components. Again, the way that we do a 2D equilibrium, break down to component, do sum of f of x equal to 0, sum of f of y equal to 0. From there, you can find your 2 unknowns. This is the component method. So now, I break the FBC on the x. This is the x-axis. And that's the y-axis. So on the x, I have FBC 4 over 5. On the y, I have FBC 3 over 5. In the other side, for AB, cosine is going to be on the x, sine is going to be on the y. So I move on. Then I do sum of f of x equal to 0. I guess my pen is gone too far on that sum. So sum of f of x equal to 0. I'm going to get this force, which is in the direction of negative, plus FBC 4 over 5 equal to 0. Then from here, you get this relationship. If I simplify it, I'm going to get FAB is equal to 1.6 FBC. On the y, I have the sine. I have the AB sine. And then, I have the AB sine 60. I have the FBC 3 over 5. They are going to the positive y, minus 80 times 9.81. And that's what I did for the y. 2 unknowns, 2 equation. You can solve for it. So it's a little bit of substitution to find FBC. And then from there I can find FAB. Again, the structure is very clear. You can follow it. Then in order, again, I know the force. I know the diameter. I want to find the stress. Kind of a straightforward. Now I put it here. FAB is this much Newton. And then I have the diameter for AB. Again, I can calculate them here. That's what I did. I know that the area for AB is pi dAB to the power of 2 divided by 4. Then from here, the diameter used to be, again, is given to us at 10 millimeter. I'm going to put it here. and the unit that I'm going to get here is meter square. Same thing for the A for BC. The area, I forgot to put the BC here. ABC is pi d to the power of 2, that's dBc, which is given to us at 8 millimeter. I found the area for BC as well. Remember to bring everything down to meter, everything else down to Newton, just to stay safe, right? And then your final answer is going to be on the Pascal. So we can calculate sigma AB, which is FAB over AAB, and then similarly sigma BC, which is FAB, what we calculated through statics. Now we bring it here to mechanics of materials to find the stress. So now, if you want to go and design the two cables down here, the two cables to hold this structure, you know the stress inside of them. Then you can actually select the material based on those stress. What I have here, for instance, I got the stress of 7.86 and 8 megapascal. Wood could be, again, something even weak as the wood would be good. I'm not going to, these are cables, I'm not going to use wood, but I can go and check the strengths of different cables and see what I need to use. You don't need to use like something like steel, because the steel is 250 megapascal. I don't need, that's going to be like a safety factor of around like 50, 60. We don't need to use that much safety factor. So in the second example, I'm going to go a little bit more into calculation of forces with respect to a little bit of thinking of where to go. So in this example, that what you could see, I have a bar AB that holding the vertical structure, the member AC. If we apply the force 3 Newton there, what would happen is that I need to know how much the force in AB is applied. So the question asks me that determine the position of X so that the average tensile stress on the rod AB, the compressive stress at the smooth support C is equal to the average stress, tensile stress in rod AB. We know the rod has a cross-sectional area of 400 millimeter, and then the contact area at C is 450 millimeter square. So I'm looking into, again, there are two forces. I need to find the direction of the X. Again, the way the question looked like, it wants me to get the sigma AB, the stress at the bar AB, is equal to sigma at C. So these two needs to be equal to each other. Now, how I equate them? I know sigma is F over A, FAB over AAB, and then FC over AC. I'm going to use this relationship. To find, like for instance, this goes back again to statics. In statics, we have three equations when we're solving problem. One was sum of moment equal to 0. Again, we are talking about rigid body 2D equilibrium. We have sum of f of x equal to 0, sum of f of y equal to 0, and sum of moment equal to 0. On the x, there is no force. On the y, FAB, and then FAB plus FAB plus FC minus 3 equal to 0. That will be on the y. If I do moment about point E, I'm going to get FAB. If you do moment about this point, moment about point E, I'm going to get FAB times this distance, which is x. That's going to go clockwise, so I'm going to use the minus for that. The force FC, that's going to go positive, and the distance for that will be 200 minus x. I'm not going to put 200. I'm going to put, again, in this case, I put 200 because everything that I do is the x that I'm going to calculate will be in millimeter too. So we continue from these equations. We have FAB, we have FC. Then from here, I found one relationship. Sorry, this relationship here is coming from this one. I have one relationship down here. FAB over AAB. AAB is given to us 400, and then the area at C is 650. So I'm going to get to this equation. FAB over 400 is equal to FC over 650. If you simplify it, you get to this relationship. Then I can use this relationship into that equation for moment to calculate the x. So that will be easy to go. And then to finish the calculation, remember we have three unknowns, right? We don't know FAB, we don't know FC, we don't know X, and then that's why we need three relationships to being able to get it done. Okay, I'm done with the first video. Thank you very much for listening to me. And then from here on, what we're gonna do in the next lecture. In the next lecture, I would be looking into, if I apply the force, how much elongation would be, and then we go ahead from there.